the invisible tether. You are falling right now. Not metaphorically, not philosophically, literally. You are falling through space-time at nearly the speed of light, and the only reason you don't notice is because the floor is in your way. This is not poetry. This is physics. And for 300 years, we've been lying to ourselves about what gravity actually is. We've called it a force. We've called it attraction. We've drawn diagrams with arrows pointing down, as if the Earth reaches up through empty space and grabs you by your ankles. But here's the truth that will unravel everything you think you know. Gravity is not a force. There is no pull. There is no invisible tether connecting you to the center of the Earth. What we call gravity is geometry. It is the shape of reality itself. And the man who understood this better than anyone, who could strip away the mathematics and show you the naked structure of the universe, was Richard Feynman. Not Einstein, not Newton, Feynman. Because Feynman had a gift that neither of them possessed. He could make you see it. He could take the most profound truths about reality and translate them into the language of human intuition. Today, we're going to destroy your conception of gravity. And then we're going to rebuild it from nothing. Let's begin with the lie. The year is 1687. Isaac Newton publishes the Principia Mathematica, and in it he commits an act of intellectual violence so spectacular that it will haunt physics for centuries. He describes gravity as a force, a mysterious attraction between masses. Every object in the universe, he claims, pulls on every other object with a strength that depends on their masses and the distance between them. The equation is elegant. The predictions are perfect. The orbits of planets, the trajectory of cannonballs, the swing of pendulums, all of it falls into place with mathematical precision. There's just one problem. It's magic. Newton himself knew this. He called it action at a distance, and he hated it. How does the sun reach across 93 million miles of empty space and grab the Earth? How does it know the Earth is there? How does the force transmit instantaneously across the void? Newton had no answer. He wrote famously, "I frame no hypotheses." Translation, I have no idea how this works. I'm just telling you what it does. And for 200 years, physicists shrugged and said, good enough. But it wasn't good enough. Not for Einstein. In 1907, while working as a patent clerk in Bern, Albert Einstein had what he would later call the happiest thought of my life. He imagined a man falling off a roof, and he realized something extraordinary. The man feels nothing. No gravity, no force, no pull. The man is weightless. If he drops his keys, they fall beside him, floating as if in space. He is, for those brief seconds before impact, in perfect free fall. And in that moment of free fall, Einstein realized the man is not being acted upon by any force at all. He is simply moving along the natural path through space-time. Gravity, Einstein understood, is not a force pulling you down. It is the curvature of space-time pushing the ground up to meet you. This is the insight that will destroy everything. Let me say it again, slower this time, because this is where most explanations fail. You are not being pulled toward the Earth. The Earth is accelerating upward into you. No. Wait. That's not quite right either. The truth is stranger. Space itself, the fabric of reality, is curved near massive objects, and you, moving through that curved space, naturally follow the straightest possible path. But in curved space, straight lines are not straight. They bend, they loop, they spiral inward. And that bending, that deviation from what you think is a straight line, is what we call gravity. This is Einstein's general theory of relativity, published in 1915, and it is the most beautiful idea in the history of human thought. But here's the problem. Nobody can visualize it. Einstein could manipulate the mathematics. He could write down the field equations, solve for the metric tensor, calculate the geodesics. But ask him to explain it to a child, and he would struggle. Enter Richard Feynman. Feynman arrives on the scene decades later, a wisecracking genius from Queens, New York, who has already revolutionized quantum mechanics and won a Nobel Prize. But Feynman's real gift is not mathematics. It's clarity. He has an almost supernatural ability to take complex ideas and distill them into images so vivid, so precise, that they bypass your intellect and speak directly to your intuition. And when Feynman explains gravity, he does it with a beetle. Imagine, he says, a beetle crawling on the surface of a bowling ball. The beetle is a two-dimensional creature. It cannot look up or down. It has no concept of the third dimension. Its entire universe is the curved surface beneath its feet. Now, this beetle wants to walk in a straight line. So it starts crawling forward, never turning left or right, always moving in what it perceives to be a perfectly straight path. But here's the trick. The surface is curved. So even though the beetle never turns, even though it always moves straight ahead, it will eventually return to its starting point. From the beetle's perspective, it walked in a straight line. From our perspective, watching from above, it walked in a circle. The beetle is not being pulled by some mysterious force. There is no invisible tether guiding it around the ball. It is simply following the geometry of the surface. This, Feynman says, is gravity. You are the beetle. Space-time is the bowling ball. And what you call falling is just you trying to move in a straight line through curved space. But wait, if gravity is just curved space, why do you fall down and not sideways? Why do objects accelerate as they fall? Why does an apple drop from a tree instead of just floating there, motionless on its curved path? This is where most explanations stop. They wave their hands and talk about geodesics and world lines and hope you don't notice they haven't actually answered the question. But Feynman doesn't stop, because Feynman knows the secret that most popular science videos never tell you, the secret that makes everything click into place. It's not the curvature of space that makes you fall. It's the curvature of time. The happiest thought. Let's go back to that man falling off the roof. Einstein's happiest thought. Why was it so revolutionary? Because it revealed something that had been hiding in plain sight for centuries. When you stand still on the surface of the earth, you feel weight. You feel the ground pushing up against your feet. You interpret this as gravity pulling you down. But here's what's actually happening. You are trying to move through time. Yes, time. Every object in the universe, at every moment, is rushing through space-time at a constant speed. Not through space, through space-time. And that speed is always the same, the speed of light. When you're standing still, not moving through space at all of your motion is through time. You are racing through the time dimension at 299,792,458 meters per second. The speed of light, this is not a metaphor. This is literal. You are a four-dimensional object moving through four-dimensional space-time, and your total velocity through space-time is always constant. When you move through space, you move a little slower through time. This is time dilation. This is why time slows down near the speed of light. But right now, standing still, you are moving through time at maximum speed. And here's the trick. Near a massive object like Earth, time itself is curved. Time flows slower near the surface of the Earth than it does in space. Not by much. Just 45 microseconds per day, but enough. And because time flows slower down here, your path through space-time bends. You are rushing through time at the speed of light, but time near the ground is slower than time near your head. So your trajectory through space-time curves. It tilts. It bends inward toward the place where time flows slower. And that bending, that tilting of your path through time is what we call falling. Read that again. You fall toward the Earth because time flows slower at the Earth's surface than it does above your head. This is gravity, not space curvature. Time curvature, or more precisely space-time curvature, but dominated by the time component. Feynman understood this. He could see it. He could show you, with just a diagram and a few words, why you fall. Imagine, he would say, 2 clocks, one at your feet, one at your head. The clock at your feet ticks slower, just a tiny bit slower, because time flows slower in a gravitational field. Now imagine you are moving through time, and your feet are aging slower than your head. Your entire trajectory through space-time must tilt to accommodate this difference. And that tilt, that bending of your motion through time, manifests as acceleration through space. You fall, not because space is pulling you, but because time is pushing you. Let's make this even more concrete. Stand up. Right now. If you're sitting, stand up. You are stationary in space. You are not moving left or right or forward or back, but you are moving through time. 1 second per second, you are aging. You are progressing through the time dimension. Now here's the key insight. In flat, empty space, far from any massive objects, your path through time would be perfectly straight. You would just sit there, hovering in space, aging normally, moving through time at a constant rate. But you're not in flat, empty space. You're near Earth, a massive object. And massive objects warp space-time. Specifically, they warp time. They make time flow slower near their surface. So right now, the space at your feet is experiencing time slightly slower than the space at your head. This creates a gradient, a slope, a tilt in the fabric of space-time. And because you are moving through time, because you are aging, progressing forward through the time dimension, your path must follow this tilt. Your motion through time gets converted into motion through space. You fall. The ground is not pulling you down. You are falling through time. And time is curved. This is why astronauts in orbit don't feel gravity. They are falling, just like you. Their path through time is just as curved. But they're moving sideways fast enough that as they fall, they keep missing the Earth. They are in freefall, following their natural geodesic through curved space-time. And in freefall, you feel nothing. No force, no pull, no weight. Just the pure geometry of space-time carrying you along. This is what Einstein meant when he said gravity is not a force. Forces, in physics, are things you can feel. You can feel electromagnetic force when you push against a wall. You can feel friction when you slide across the floor. But gravity? You never feel gravity. What you feel is the ground pushing back, the electromagnetic repulsion of atoms preventing you from falling through the floor. Gravity is the absence of force. It is the natural motion through curved space-time. And standing still on the Earth's surface is like being pinned down, prevented from following your natural path. You are not at rest. You are being accelerated upward by the ground, held in place against your will, prevented from falling freely through space-time. This is why you feel weight. Not because gravity is pulling you down, but because the ground is pushing you up. The geometry of the Beetle. Now comes the hard part. How do you visualize this? How do you see the curvature of space-time when you are stuck inside it, like the Beetle on the bowling ball? Feynman had an answer. He said, you measure triangles. In flat space, the angles of a triangle always add up to 180 degrees. Always. Perfectly. Forever. But in curved space, they don't. Draw a triangle on the surface of a sphere, say, the Earth. Start at the equator. Draw a line north to the North Pole. Turn 90 degrees. Draw a line back down to the equator. Turn 90 degrees. Draw a line back to your starting point. That's a triangle. 3 sides, 3 corners. Now add up the angles. 90 degrees, 90 degrees, 90 degrees. 270 degrees. Not 180, 270. The triangle is bloated, swollen, curved. This is how you detect curvature. Not by stepping outside and looking at the whole thing from above, but by measuring from within. You draw triangles. You measure angles. And if they don't add up, you know space is curved. This is what Einstein's field equations describe. They tell you how mass and energy curve space-time. They tell you how much the angles deviate, how much the geodesics bend, how much clocks slow down. But they don't tell you why. They don't tell you what space-time is made of. They don't tell you why mass curves it. They just describe the relationship, the geometry. Mass tells space-time how to curve. Space-time tells mass how to move. It's a loop, a feedback mechanism, a dance between matter and geometry. And for 100 years, this description has been enough. General relativity predicts the bending of starlight around the Sunday. It predicts the precession of Mercury's orbit. It predicts the existence of black holes, gravitational waves, the expansion of the universe. Every prediction has been confirmed. Every test has passed. It is, without question, the most successful theory of gravity ever conceived. But it is incomplete, Because there's another theory, another description of reality, quantum mechanics. And quantum mechanics says something very different about the nature of space and time. In general relativity, space-time is smooth, continuous, a perfect geometric manifold. In quantum mechanics, everything is discrete, pixelated, made of chunks. Energy comes in packets. Angular momentum comes in units. Even space itself, quantum mechanics hints, might come in pieces. At the smallest scales, the Planck length, 10 to the negative 35 meters, space-time might not be smooth at all. It might be foamy, turbulent, boiling with quantum fluctuations. And this is where the two great theories of physics collide. General relativity describes gravity as smooth geometry. Quantum mechanics describes everything else as discrete particles and fields. And nobody knows how to reconcile them. Feynman spent years trying. He developed quantum field theory. He quantized electromagnetism, the strong force, the weak force. But gravity resisted. Every attempt to apply the same techniques to general relativity led to infinities. Nonsensical answers. Mathematical catastrophes. Feynman called it the only real failure of my career. He never solved it. Nobody has. To this day, we have no quantum theory of gravity. We have candidates. String theory, loop quantum gravity, causal set theory. But no proof, no experiment, no confirmation. Gravity remains the orphan of physics, the one force that refuses to play by quantum rules. And this is not just an academic problem, because at the center of a black hole, where space-time curvature becomes infinite, general relativity breaks down. And at the moment of the Big Bang, where all the mass in the universe was compressed into a quantum scale point, general relativity breaks down. In these places, we need a quantum theory of gravity. And we don't have one. The time dimension. Let's go deeper. Let's talk about what it really means to move through time. You think of time as something that happens to you, a river carrying you forward, a clock ticking in the background while you live your life. But that's not what time is. Time is a dimension, like length, width, height, another axis, another direction you can move through. And right now, you are moving through it at the speed of light. Think about what that means. Every second you age 1 second, you progress 1 second into the future. That is motion, real motion, through a real dimension. And like all motion, it has a speed. 1 second per second, which, if you convert the units, is 299 million meters per second, the speed of light. This is why the speed of light is the speed limit of the universe. Because it's not really the speed of light. It's the speed of space-time, the speed at which all objects move through the four-dimensional fabric of reality. Photons move through space at the speed of light, which means they don't move through time at all. Time stands still for a photon. You move through time at the speed of light, which means you don't move through space very much at all, not compared to the speed you're moving through time. And when you do move through space, you slow down through time. This is time dilation. This is relativity. This is the deep structure of the universe. Now add curvature. Near a massive object, time flows slower. Clocks tick slower. Processes run slower. Aging happens slower. This has been measured. Atomic clocks on airplanes tick faster than atomic clocks on the ground. GPS satellites have to account for this. If they didn't, your navigation would drift miles off course every day. Time curvature is real. It is measurable. It is not a metaphor. And because you are always moving through time, always aging, always progressing forward, this curvature affects you. Your motion through time must follow the curve. And when time is curved inward, when it flows slower near the Earth, your motion through time tilts. It gains a component in the space dimensions. You start moving downward. You start falling. Not because something is pulling you, but because the shape of time itself is guiding you. Feynman had a way of visualizing this. He would draw a graph, time on the vertical axis, space on the horizontal. Your motion through time is a vertical line, straight up, aging 1 second per second. Now tilt the time axis inward, curve it toward the Earth. Suddenly, your vertical line is no longer vertical. It's slanted. It has a horizontal component. You are moving through space. You are falling. Not because any force is acting on you, but because the geometry of space-time has tilted. This is the essence of general relativity. Curvature equals acceleration. Geometry equals gravity. But here's where it gets truly strange. If you're falling freely like an astronaut in orbit, like a person jumping off a diving board, you don't feel this at all. You are weightless. You are moving along a geodesic, the straightest possible path through curved space-time. From your perspective, you are not accelerating. You are not changing velocity. You are simply floating, drifting, existing. It is only when something prevents you from following your geodesic, like the ground pushing up against your feet, that you feel acceleration. You feel weight. So the question is, who is really accelerating? The person standing still on the ground, or the person falling freely through space? Einstein's answer is shocking. The person standing still is accelerating. The person falling is not. The ground beneath your feet is pushing you upward at 9.8 meters per second squared, preventing you from following your natural path through space-time. You are being accelerated upward, constantly, every moment you stand here. And that upward acceleration is what you call weight. This is the equivalence principle, Einstein's first great insight. There is no difference between gravity and acceleration. Standing on the Earth feels exactly the same as standing in a rocket accelerating through space at 9.8 meters per second squared. Not similar, identical, because they are the same thing. You are being accelerated upward by the ground. And the only reason you don't fly off into space is because the rest of the Earth is in the way. This is why Feynman loved general relativity. Because it takes something you thought you understood standing still and reveals it to be something completely different. You are not still. You are accelerating. You are not at rest. You are being pinned in place, prevented from following your natural geodesic, held captive by electromagnetic forces in the ground, pushing back against the electromagnetic forces in your feet. Gravity is geometry, and you are a prisoner of that geometry. The black hole edge. Now we arrive at the abyss, the place where geometry breaks. Black holes. A black hole is what happens when you compress mass so densely that space-time curvature becomes infinite. Not very large, infinite. At the center of a black hole lies the singularity, a point of infinite density, infinite curvature, infinite tidal forces. And at that point, general relativity collapses. The equations spit out infinities, nonsensical answers, mathematical screams of protest. This is where we need quantum gravity. And we don't have it. But even before you reach the singularity, even outside the black hole, the geometry does something extraordinary. It bends so severely that time and space swap roles. Outside a black hole, you can move through space in any direction you want. Left, right, forward, back, you have freedom. But you cannot move backward through time. Time flows forward, always, inexorably. Inside a black hole, this reverses. The inward direction, the direction toward the singularity, becomes time-like. You cannot avoid it, you cannot stop, you cannot turn around. Just as you cannot avoid moving forward through time outside the black hole, you cannot avoid moving inward inside the black hole. The singularity is not a place. It is a moment, a point in your future, inevitable. Once you cross the event horizon, you do not fall into the singularity. You age into it. This is the geometry of a black hole, and it reveals something profound about the nature of space-time. Curvature is not just bending, it is transformation. Near a black hole, the dimensions themselves change character. What was space becomes time. What was time becomes space. And this is not metaphor. This is not analogy. This is what the mathematics of general relativity tells us happens. Feynman was fascinated by this. He spent years studying black holes, trying to understand what happens at the event horizon, what happens at the singularity. He never found a satisfactory answer, because the answer requires quantum mechanics, and quantum mechanics doesn't describe gravity. We are stuck. But black holes have taught us something else, something even stranger. They evaporate. In 1974, Stephen Hawking proved that black holes emit radiation, slowly, imperceptibly, but inevitably. They lose mass, they shrink, and eventually they disappear. This is quantum mechanics intruding on general relativity. At the event horizon, quantum fluctuations create particle-antiparticle pairs. One particle falls in, the other escapes. The black hole loses energy. It evaporates. And when it does, what happens to the information that fell in? The books, the people, the planets, everything that ever crossed the event horizon, where does it go? Does it disappear, erased from the universe forever? Or does it somehow escape, encoded in the radiation? This is the black hole information paradox. And after 50 years, we still don't know the answer. Feynman didn't know. Hawking didn't know. We don't know. Because to answer it, we need a theory that unifies general relativity and quantum mechanics. And we don't have one. The unfinished symphony. So where does that leave us? We have a theory, general relativity, that describes gravity as the curvature of space-time. It works perfectly for everything we can measure. But we know it's incomplete because it doesn't incorporate quantum mechanics, and everything else in the universe is quantum. Electrons are quantum. Photons are quantum. Atoms, molecules, chemistry, biology, all quantum. Even empty space is quantum. The vacuum seethes with virtual particles, fluctuating fields, quantum foam. But gravity? Gravity remains classical, smooth, geometric. And this cannot be the final answer. Feynman knew this. In his later years, he gave a series of lectures on the character of physical law. And in one of those lectures, he said something remarkable. He said, "We do not know where we are, stupid." We have these two great theories, general relativity and quantum mechanics. Both are correct. Both make perfect predictions within their domains. But they contradict each other at the deepest level. One says space-time is smooth. The other says everything is discrete. One says gravity is geometry. The other says forces are carried by particles. And we don't know which one is wrong. Or if both are wrong, or if there's some deeper truth, some more fundamental theory that contains both as special cases. String theory tried. It proposed that particles are not points but tiny vibrating strings, and in this picture, gravity emerges naturally. The graviton, the hypothetical quantum particle of gravity, is just a particular vibration of the string. It was elegant. It was beautiful. It unified all the forces. But it required extra dimensions, 10 dimensions, 11 dimensions, dimensions we've never seen. And it made no testable predictions. No experiments could confirm or refute it. 50 years later, string theory remains a promising idea. But not a proven theory. Loop quantum gravity tried a different approach. It said space-time itself is quantized. Space is made of discrete chunks woven together like a fabric. Geometry is quantum. Area and volume come in minimum units. It was radical. It was mathematically rigorous. But it couldn't reproduce general relativity in the classical limit. It couldn't explain why space-time looks smooth at large scales. And it too made no testable predictions. Feynman would have hated this. He was a pragmatist. He believed theories should make predictions. They should be tested. They should be confirmed or thrown out. He once said, "It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong." And right now, we have no experiments that can test quantum gravity. The energies required are too high. The distances too small. We would need a particle accelerator the size of the galaxy, or a microscope that can see the Planck length. We have neither. So we are stuck, guessing, theorizing, building mathematical castles with no foundation in reality. This is the unfinished symphony, the greatest unsolved problem in physics. How do you quantize gravity? But maybe we're asking the wrong question. Maybe gravity is not a force to be quantized. Maybe it's something else entirely. An emergent phenomenon, a collective behavior that arises from something deeper. There are hints of this. Thermodynamics, for instance. The study of heat and entropy. Nobody thinks temperature is fundamental. Temperature emerges from the motion of molecules. Maybe gravity is similar. Maybe it emerges from the quantum behavior of space-time itself. This is the idea behind entropic gravity, behind holography, behind the notion that the universe is fundamentally made of information, not matter. And these ideas lead somewhere extraordinary. They lead to the possibility that space-time itself is not fundamental, that at the deepest level there is no space, no time, no geometry, just information, just quantum bits, just relationships between events. In space-time, the stage on which all of physics plays out is an illusion, an emergent property of something more fundamental. This is where we stand today, on the edge of understanding. We know gravity is geometry. We know quantum mechanics is real, but we don't know how to put them together. We don't know what space-time is made of. We don't know if it's made of anything at all. We don't know why mass curves space-time. We don't know why curvature produces gravity. We can describe it. We can measure it. We can predict it. But we cannot explain it. Not yet. Feynman understood this humility. He knew that every answer leads to deeper questions. Why does mass curve space-time? Because of the stress-energy tensor. But why does the stress-energy tensor curve space-time? Because of the Einstein field equations. But why do those equations describe reality? We don't know. At some point, the chain of whys ends, not because we've reached the final answer, but because we've reached the edge of our understanding. And that edge is where physics lives. So what can we say? What do we actually know? We know that gravity is not a force. We know that space-time is curved by mass and energy. We know that we move through time at the speed of light, and that this motion curves near massive objects, creating what we call falling. We know that geodesics, the straightest possible paths through curved space-time, are what free-falling objects follow. We know that standing still on the Earth is not standing still at all, but being accelerated upward, prevented from falling. We know that black holes exist, that they warp space-time so severely that even light cannot escape, and that they evaporate through quantum processes we barely understand. We know that general relativity and quantum mechanics are both correct and both incomplete. And we know that somewhere in the mathematics we haven't yet discovered there is a deeper truth, a theory that contains both. A theory that explains not just how gravity works, but why. Feynman never found it. Einstein never found it. Hawking never found it. Maybe someone alive today will find it. Maybe it will take another century. Or maybe, and this is the possibility that should excite you most, maybe we're asking the wrong questions entirely. Maybe gravity is not a puzzle to be solved. Maybe it's a doorway, a portal to a deeper understanding of what the universe is. Because if gravity is geometry, and geometry is quantum, and quantum is information, then what is the universe made of? Not matter, not energy, not even space-time. Information, relationships, correlations, quantum entanglements, woven into a tapestry so intricate, so complex, that it gives rise to space and time and matter and gravity as emergent phenomena. This is the frontier. This is where we're headed. And when we finally understand it, when we finally see the deep structure beneath the surface, it will change everything. Not just physics, not just cosmology, but our understanding of what it means to exist in this universe. Because here's the final, most profound truth. You are not in the universe. You are not separate from space-time, moving through it like a boat on a river. You are space-time. You are a pattern in the geometry, a ripple in the fabric, a localized curvature moving through the manifold. When you fall, you are not being pulled by gravity. You are following the shape of yourself. When you age, you are not moving through time. You are time flowing. This is what Feynman understood. This is what he tried to show us, that the universe is not made of things. It is made of geometry, of relationships, of patterns. And you, with your thoughts and your dreams and your questions, are one of those patterns, a particularly complex one, a self-aware one, but a pattern nonetheless. Gravity is not something acting on you. It is you being what you are in a universe that is curved. So the next time you drop something, watch it fall. And remember, it is not being pulled down. It is following a geodesic through curved space-time. It is moving in a straight line through a geometry you cannot see. It is doing exactly what you are doing right now. Rushing through time, aging, existing. And in that moment, you will glimpse what Feynman saw. The universe is not a mechanism. It is a geometry. And you are part of that geometry. Not a visitor, not an observer, a participant, a pattern in the fabric, a wave in the ocean of space-time. And that is gravity. Not a force, not a pull. But the shape of reality itself